everyone, my name is Grace Mulry and I am presenting today with Kayla Barker on a bipartite graph reduction game and its association with double Choco puzzles. We worked on this project in collaboration with Garrison, Koch, Kyla, Shappell, and Kathleen Ryan. So first we're going to introduce the bipartite graph game. We'll then discuss the relationship between the solvability of the game and a certain sum condition. We'll then explore properties of the game on trees and even cycles. And to end, we'll examine the connection between the bipartite graph game and the double Choco puzzles. So in particular, while working on this project, we looked at bipartite graphs, but especially the graph classes of paths, trees, and even cycles. We define a game labeling of a bipartite graph G as a labeling L of the vertices of G such that L of V is non-negative for each vertex V, and the partite sets of G have equal label sum. So if you look at this example here, can you figure out which bipartite graph has a game labeling? I'll let you pause the video. And it's going to be the one on the left. The reason is, in one set, we have our white vertex, which has a label of 6. And our other set, we have our 3 gray vertices, and the sum of their labels, 2, 3, and 1, will also be 6. So how do you play the bipartite game? So the first thing you do is subtract the labels of any 2 adjacent vertices by the same amount, and that's referred to as a reduction. Note that reductions cannot yield negative labels. Then you'll continue reducing labels between adjacent vertices until no valid reductions are possible. If all vertices have a label of 0, then you've won the game. But if any vertices have non-zero labels, you have lost. So here's an example of playing the bipartite graph game. So this is the graph from before. The first thing we're going to do is reduce the 2. And then we'll reduce the 3. And we'll end by reducing the 2 1s. In this example, there was no way to lose the game. However, there are examples where players don't win, even though a winning series of reductions does exist. So you can see here, this player has played the game in such a manner that they ended up with a gray vertex labeled 1 and a white vertex labeled 1, but they're not adjacent to each other and they can't be reduced. However, if they had played it a little differently and started in the same point, but worked counterclockwise with their reductions rather than clockwise, they would have been able to win the game. We say a bipartite graph with a game labeling is solvable if there exists a series of reductions that lead to a labeling of all zeros. If a bipartite graph with a game labeling is impossible to win, then it is unsolvable. A natural question that arises is, does every bipartite graph have some game labeling that makes it solvable? And our answer is yes. The reason being is that we can generate solvable labelings using degrees. And we have this lemma that says labeling each vertex in a bipartite graph G with its degree yields a game labeling, and furthermore, G with this game labeling is solvable. The basic idea of the proof of this lemma is that you can label each edge 1 and reduce adjacent vertices to each edge by 1. And by reducing in this manner, because the vertices are labeled with degrees, you're always going to win the game. So we also, when examining which labelings were solvable, came across the idea of a basic sum condition. So let G be a game labeled bipartite graph. If G under the given labeling is solvable, then for all vertices V and G, the label of V is at most the sum of its neighbors' labels. And then that's just some notation. So if you look at the graph in this picture, we can see that it is not solvable. And we can see by looking at this highlighted 3 in red, the 3 surpasses the sum of its neighbors because 3 is greater than 2. And because of this, the graph is not solvable. So the basic sum condition is more of a local one that checks that nearby neighbors meet a certain property. And we found that a more general sum condition was needed to prevent some issues created by more spread out vertex sets. So here's an example. This tree does meet the basic sum condition, but it's not solvable. We label the set S, or we make the set S be X and Y, and we can see that the label sum of S is 7. The label sum of the neighborhood of S, however, is only 6. So we can see that the label sum of the neighborhood of S has to be larger than 7 to solve the game. And from here arose a theorem. Let G be a game labeled bipartite graph. If G under the given labeling is solvable, then for every subset S of vertices in a partite set, the sum of the labels in S is at most the sum of its neighbors' labels. And there's some notation. So looking at the graph below, can you figure out which subset of the gray vertices fails the GSC? Go ahead and pause the video and see if you can find it. So it's actually going to be these 3 gray vertices, the 4, and the 3. You can see that their label sum is 11. However, the label sum of their neighborhood is just 10. We have a conjecture that the GSC is necessary and sufficient, meaning that G under the given labeling is solvable if and only if the GSC holds. Our progress on this conjecture so far, we've proven it for the case of trees, we've proven it for the case of even cycles, and we're working on proving it for bipartite graphs in general. So I will let Kayla take it away from here.
Okay, so we have proven that the generalized sum condition is sufficient for trees. The idea of this proof is by induction on the number of vertices. So we want to start with the leaves on the outside and reduce what those labels on those leaves are and work inwards. A result from this is that we have also proved it for paths. Something that arose while working with the sufficiency of trees is the idea of a cut edge. We have found that all trees have cut edges, and a cut edge is an edge that you can remove and you will make 2 disjoint graphs from the overall graph. So when working with cut edges, we find that you can determine what the reduction across that edge must be by looking at the sum of the labels of the gray vertices and the sum of the labels of the white vertices on both of the disjoint sets. And whatever the difference is, if they are equal, then that is what the reduction has to be across that edge. In this example, you can see on the left side that there is a difference by 2, and on the right side, there's a difference by 2. Therefore, the reduction across this edge must be 2. So something that cut edges tells us is that there is one unique solution when playing the game on trees. And then even though the order of the reductions can differ, the set of reductions performed across the edges will always be the same. We have also proven that the generalized sum condition is sufficient for even cycles. The proof sketch for this is that we remove an arbitrary edge, UV, where U is the gray vertex and V is the white vertex. This yields a path. If the generalized sum condition still holds, a solution exists for the path by the tree proof, and the solution to the path gives a solution to the original cycle. You can see that that is the set of reductions made for this solution. Otherwise, the generalized sum condition does not hold when UV is removed. Any subset of vertices from the white partite set that fails the generalized sum condition must contain V, and we can argue that without loss of generality, we may assume that a set S is a chain from V, where a chain is a series of consecutive vertices in a partite set. We find a chain S from V with the maximum generalized sum condition failure amount. We denote that as delta V. So in our example below, our maximum generalized sum condition failure is equal to 3, and that occurs with these vertices here that are highlighted, where the sum of its labels is 9 and the sum of its neighborhood is only 6. So there's a difference of 3. We then divide U into 2 non-adjacent vertices, one connected to V and labeled delta sub V, and the other one replacing U with the label U minus delta sub V. We can show that the generalized sum condition holds in this path. Again, by the tree case, we know that a solution exists, which gives us a solution to the original cycle. While working with cycles, we notice that solutions always seem to have an extraneous edge. And an extraneous edge is an edge that is not pertinent to the solution. So we have a theorem that if a solution exists to a game labeled even cycle, then there exists at least one extraneous edge. Following that, if a solution exists to a game labeled bipartite graph, then every even cycle within the graph also has an extraneous edge. The way that we find extraneous edges is that you already know the set of reductions that you need to make on the graph. So you can put weights on the edges that correspond to the reductions that need to be made across those edges. So we've gone ahead and done that for this example. Now you want to find the weight that is the lowest value. In this case, it's a 1. You could choose any of them, but in this example, we start with the top one. And what you're going to do is you're going to subtract 1 from that weight, and then going in a counterclockwise or clockwise fashion, as long as it's in the same direction. You're going to then add 1 to the following edge, and then subtract 1. And then add 1, and then subtract 1. You do this with the smallest value. So in this case, it's 1, but in any other case, it could be 2, 3, whatever works. So you go ahead and you end up with this, and any weights that are left with 0 are extraneous. And you can follow the same process in a bipartite graph. So we know that the generalized sum condition is sufficient for trees, paths, and even cycles, and we are working on showing that it is sufficient for bipartite graphs in general. We have a partially complete proof using similar ideas shown in the even cycles proof. We just have one case of that left to finish, and our hope is to also find a proof where we can remove an extraneous edge from every cycle and reduce the bipartite graph to a tree. So how did we come across our game? Well, we came across it while solving double Choco puzzles. Double Choco puzzles are played on square boards, and it consists of an even amount of gray and white cells. The object is to draw borders around blocks of cells of the same shape and size, and it has to have 1 of gray cells and 1 of white cells. And you want to do this for the entire board so that no cells are left out. And something to note is that the shapes can be mirrored or rotated or reflected. And another thing to note is that there can be multiple solutions. This is just an example of one solution to this board. So not every board with an equal number of white and gray cells has a solution. This is an example of an unsolvable double Choco puzzle. We will discuss why it is unsolvable in a couple slides. So to get the bipartite graph from a double Choco board, first we need to map a double Choco puzzle to a dual graph. So this is no longer the solutions, but now just the regions of cells of same colors. So you want to count the number of cells in each region, and each region will correspond to a vertex on a graph, and the label will correspond to the number of cells that were in that region. And then on the board, if two regions are touching, they will share an edge on the graph. So a dual graph of a double Choco puzzle is a game labeled bipartite graph because it is bipartite, and it is game labeled because it comes from the double Choco board, which we know has equal amounts of gray and white cells. So this is the solution to the board that we saw earlier, and then this is its mapped dual graph. And something that you can see here is that a double Choco puzzle, if it is solvable, then the bipartite graph game played on the dual graph will be solvable. The reason for this is that you can see this region of 6 cells here. You can see what reductions must be made because it's broken up into 1, 3, and 2 cells here. So on this edge, you would need to reduce it by 2 corresponding here, and this edge, reduce it by 3 corresponding here, and here there's a 1. So that's the reduction there. And then you follow through with the rest of the graph. And here you can see that we have a larger double Choco puzzle. This is the one that we saw before. And so one of the things we wanted from our dual graphs was to help us determine easily if there was a solution or not to a double Choco puzzle. So if you know right away that the dual graph fails and there's no solution, then you will know that the double Choco puzzle has no solution. So in this case, this bipartite graph here, the dual graph of this double Choco board, fails the generalized sum condition, and you can find it in this top left corner. We have a 5 label here, and its neighborhood is only equal to 4, so it fails. If you look back at the board, you'll see that this region has 5 cells here, and it is only connected to 4 gray cells. Therefore, they cannot be matched, and there is no solution. So now we have seen that if you have a solvable double Choco board, it results in a solvable dual graph. If you have an unsolvable dual graph, it results in an unsolvable double Choco board. However, if you're given a dual graph that is solvable, you don't know if the double Choco board is going to be solvable or not. The reason for that is that the dual graph only takes into consideration the size of the regions and not like the shapes or the distances between the cells. So on the right, we have a solvable dual graph and it meets the generalized sum condition. But on the left, you see that it's a corresponding double Choco board. Over here in this corner, these 3 cells do not match up to these 3 cells because of the shape and the distance between the cells. So here you would need a distance of at least 2 because 2 cells cannot be matched by a corner. But all of the gray cells here are only of size 1, so the distances do not match. Future work, we would like to investigate which bipartite graphs are dual graphs of some double Choco puzzles. An example that we found of this is if an n cycle is a dual graph, then n must equal 4. We would like to examine the bipartite graph game as a 2-player game. We'd like to create a more informed bipartite graph game that includes double Choco board information such as the distance and shape. We'd like to generalize the bipartite graph game to a multipartite graph game. And we'd like to change the double Choco board structure to a torus and analyze if the generalized sum condition holding on the dual graph is now sufficient when the shape requirement is relaxed. We'd like to say thank you so much to the Young Mathematicians Conference for allowing us to present our work, and to Moravian University and the NSF for hosting and funding our wonderful REU experience this summer. Thank you.
Thank you all.